Hi, what I've got here for you guys on the bench today is a 1500 watts pure sine wave inverter from CNSWIPower, and it was provided to me by the manufacturer for a review. I'm going to provide a couple of links in the video description down below so you know exactly what product I'm talking about, as I saw this brand was referred to by a few slightly different names. By the way, the links provided here are just for your reference. It is by no means an endorsement to a specific seller, so if you do decide to buy one, be sure to look around as the price can vary quite a bit depending on where you buy it from. With all the logistics out of the way, let's get started. I did a review on an 800 watts pure sine inverter a few years ago, and that one was a reliable electric brand, and if you recall, I was quite impressed by the performance and construction of that inverter. Since that review, I have got to use it during the power outages many times already, and so far I haven't had any issues. So with that inverter as a reference, the bar has been set pretty high. In that video, I also discussed how a pure sine inverter works, so I'm not going to spend a lot of time on the principles of operation here. If you are interested, please check out that video. I'm also going to provide a link down below. In summary though, there are a couple of ways to implement a pure sine wave inverter. One way is to use a PWM signal to drive an inverter and at the transformer output adding a low-pass filter to obtain the sine wave. Another way, which is more common in these higher powered inverters, is to have a DC-DC converter to first convert the input to high voltage DC output, and again use a PWM signal to drive an active full bridge to produce the sine wave. Of course, the output is also low-pass filtered. What I'm going to do in this video is to first do some real-world testing and then moving on to do a full teardown to see what is inside. This inverter is a 12-volt version. In my opinion, 12-volt input is the most versatile, as in emergencies you can always hook it up to your car battery and leave your car running and use the generated power to power your electronics. But of course, for higher output powers, 12-volt input would not be as efficient as a higher voltage input due to the high running current and unavoidable resistive power loss, for example, due to the cabling. This inverter also comes with a remote control panel, which is useful if you're doing a permanent installation. It also comes with these rather stiff and short battery cables. Now, it is understandable these are short, as the maximum current can reach well above 100 amps, and the cable loss needs to be kept at a minimum. But as you can see, that the cables are also doubled up, instead of using just a single proper gauged wire. Now, I suspect this is due to the cost reduction, and they can use the same wire for different models of the inverters. Nothing is wrong with that, of course, but I do wish they could use a more flexible, finer stranded cable so that it is easier to connect to a battery. One thing to note is its physical size. When you look at the inverter, it's not that big. In fact, it's comparable to the size of the 800 watts inverter that I did a review a couple of years ago. It's only ever so slightly wider than that inverter, but it's considerably heavier, given that it probably has a better heat sinking capability inside. Now, the case is actually really sturdy, and it's by the look of it is a casted aluminum case, and it's very rigid, so I like that construction a lot. And by looking at this end, you can see that here are your battery input terminals. They are opposing each other as to prevent you from accidentally shorting out the battery when you are connecting up to the inverter here. On this end, it's quite standard. It has two outlets, and you have a voltage and amperage reading at the bottom here. And here is that remote operating terminal that I mentioned earlier. So that's pretty much all there is on this inverter. Now let me hook it up to a power source and we can do some testing here. And now I have it hooked up to an RD6012 power supply that I reviewed last time. And let's see what the no load current consumption is. Later on, I will hook it up to a battery bank and do some load testing, and also we'll see the output waveform quality under different load. Oh, I forgot to mention that this inverter also came with a product manual, and inside you can see its specifications. Now, this manual is generically made for different models, but as you can see, our model is here, and it has input low voltage and high voltage protection. So later on when we're doing testing, we're gonna see that. And also you can see here, we have, again, we have a pretty impressive specs here. So it says the output efficiency is greater than 90%. So we will have to test it during our testing later on. One more thing before we power it on, I want to take a look at if the chassis ground is connected to the earth ground pin here. So let's take a look. And it appears it does, so it's very good. Now, keep in mind that some inverters, the neutral pin actually has a output voltage, and sometimes it's 60 volts. And so for those inverters, you can't really tie the earth pin and your neutral pin together. But if you are to install your inverter to a, say, a transfer switch, that is almost always on the other end of the circuitry somewhere, the earth and your neutral are tied together. So for this one, let's first take a look at if there's any measurable resistance between these two pins. And by the look of it, it doesn't seem like there's any. So of course we have to power it on and see what the voltage differential is between these two pins. But my suspicion is this one would be able to be hooked up to your home installation. So we can give that a test as well. Okay, so now let's turn on the power supply and turn on the inverter as well. There's a little bit of delay here, and now you can see that the output voltage is ramping up. And it appears that this one also has this soft start feature, meaning the output voltage is not 120 as soon as you turn it on, but slowly ramping up to that voltage. Now that is fine for majority of the appliances, but certain electronics do not like that at all. In fact, in my last review on the 800 watts inverter, you saw that the kilowatt power meter did not like this feature. In fact, we have to recycle the meter by unplugging and replugging in order for it to work. And one thing is actually already very impressive, not sure if you can see that on the display here, is right now we're at 13 volts input voltage, and the standby current is just hovering around 400 milliamps. That's actually very, very good for a 1500 watts inverter like this one. If you recall the last one, the 800 watts one, the standby current is actually a little bit higher at, I think it was 600 to 700 milliamps. So that's really good. And of course, we wanted to measure the output voltage accuracy and the output frequency, and I have no doubt those going to be right on the to the spec as well. So let's just take a quick look here. For that, I'm going to test. So yep, so it's 101 volts, and it largely agrees with what the meter says here. And so let's take a look at the frequency as well. It's 59.7 Hertz, so it's close enough. Since this inverter has overvoltage and undervoltage input protection, let's take a look at when that is triggered. So for that, I'm going to do VSET, and I'm going to do it 0.1 volt at a time. So let's do overvoltage first. I'm going to increase it. So now it's 13.6 volts, 13.8, and it's 14 volts. It's 14.7 now. Okay, so it seems like at 14.8, that's when the overvoltage is triggered. So let's lower it down. Interestingly, as soon as we lower the voltage, you can see that it started ramping up again. Okay, so that output was cut when the input over voltage is detected. And let's lower the input voltage. Now we're at 11.6, everything is still going. And 10.43. That's actually pretty low here. 9.9. No, so now at the 9.9, actually around the 10 volts mark, the output cut off. So that's our low voltage protection. And of course, we have to ramp it back up. I'm not sure when the output is going to be re-enabled. Okay, looks like at 12.4, 12.5, the output get re-enabled again. So that's largely in line with what we see in the spec. Now the low voltage cutoff could be a little bit too low here, as if you're hooking up to a battery, the battery might be excessively drained if you don't have a good battery management system. But nevertheless, I think under load, they're taking into consideration some voltage drop over the cables, and that voltage is actually quite all right here. Okay, so now we get some general idea of the specs of this inverter, and let's hook up a beefy battery pack, and we'll do some load testing here. Now I have hooked up the inverter to a battery bank back there, and I built that battery bank a few years ago. That is a 12 volts, 1500 watt hour lithium iron phosphate battery bank. And it's capable of delivering over 150 amps, which is perfect for this inverter here. And in a test we just did a while ago, I forgot to test whether or not we can hook up the earth, ground, and the neutral together safely. And we'll do that test right now. But before I do that, let me power up again, and we'll see if there's any voltages between these two. As we measure the resistance, this seems to be high impedance, but we wanted to double check that. So let me turn it on again, and let's just do some quick measurement here before we short them together. So this is our ground pin, and this is our neutral. And right now we're not seeing any voltages, so let me just try it again. We're seeing only minimum voltages. So that's actually a very good sign. Of course, I'm going to short them together, and it could go horribly wrong, but I'm pretty confident that this is going to work. So for that, I have this cable here, and I'll show you that on this end, I basically just plugged it into a socket here, and I have the ground pin and your neutral soldered together. So I'm going to plug it in, and let's see here. Yep. So as you can see, there's no problem at all. So basically, this is definitely safe for you to plug into your home transfer switch, and in the event of a power failure, you can use this inverter to power your house. Okay, so in order to make this video not too long, I'm going to combine a lot of the tests in the same setting. So let me just quickly go over what we're testing here. And now I have the output to this inverter hooked up with a watt meter. And on the other end of the watt meter, I have a variac connected to a heater. That heater is capable of outputting well over 1500 watts, so would be definitely sufficient for testing this inverter. And on the positive cable here, I have a clamp meter so that we can monitor the current that is being consumed by the inverter. And on the other end, you can see an oscilloscope, and that is actually hooked up to the output from the inverter, so we can monitor the waveform here. And so I'm going to power on the inverter shortly, and the first thing I wanted to pay attention to is the waveform. As we mentioned, it's a slow start up, so you should be able to see that in the oscilloscope waveform here. So let me actually first just put my focus on the oscilloscope, and you can see that. I'm going to power on, So let's take a look. So now it's powered on. As you can see that the output gradually increases till it reaches the full 120 volts. Now, the output right now looks pretty clean. There is a little bit of a glitch, or it's distortion rather, at the zero crossing, but it's nothing to be concerned about, and it's fairly clean. So we will have to see what that waveform looks like once we apply some load. And of course, right now the watts up right now consumes about 6.6 watts. That's just our variac here, and nothing else is drawing any power at the moment. So now let me gradually ramp it up. By the way, I'm also going to record at various points the input voltage, the current, and also the output wattage that we recorded here, so that we can draw some conclusion on the efficiency of this meter as well. And let me actually zero it out. Sorry, that's not a zero. I can't see it. That's hold. This is zero. Okay, zero out the meter. And then I'm going to turn on the variac gradually. So now let's do it. And you can see that we're right now drawing around, let's start from 100, around 100 watts, and we're drawing about the 7.7 amps, no problem at all, and the waveform looks very good still. So let's increase it. Now it's around 200 watts. And by the way, the fan of this inverter still hasn't kicked off yet, so which means it's still operating very cool. Yeah, I can't feel any, nothing is heating up yet. Now we're drawing 17 amps, and the waveform looks still pretty decent. So let's keep increasing. Let me do 300 watts. No problem. So let me just keep increasing. Let's do 400, 500. Now we're almost reaching 50 amps on the clamp meter there. And we're drawing currently 570 watts. Everything looks still pretty normal. So let's keep increasing. So far, so good. And at roughly 700, 800 watts, you hear that the fans are kicking off, and it's actually pretty loud. But now we're drawing about 74 amps, as you can see on amp meter here, and no problem at all. So let's keep increasing. So now we're at 1100 watts, and actually it's very impressive. If you look closely at that output waveform, at the beginning I was a little concerned that it has a little bit of a distortion, but actually that distortion doesn't seem to be getting any worse. In fact, it appears it's just part of the waveform generation here, and it remains exactly the same as before, with very little distortion in fact. So right now we're at 1100 watts, and everything's still going very smoothly. Let me keep increasing the output wattage here. And we're at almost 1300 watts. Everything's still holding up. And you look at the current meter. Right now we're drawing 131 amps. Not sure if you can see that. 131 amps. Okay, so let's keep increasing, and let's see at what point we're going to trigger the load protection here. So wait a second, it's only at 1300 watts, and you heard that alarm. I'm not sure if that's just warning you it's approaching, or the limit, or it's actually exceeding the limit. but the limit should be at 1500 watts. So let's see at what point it will shut off. Let's keep increasing. So 1300 watts. So it looks like, by the look of it, the maximum wattage it can draw is only just above 1300 watts, which is a little bit short of the 1500 watts that is specified. Again, if you remember when we did the testing for the 800 watts inverter a while ago, that one also did not quite reach that 800 watts. So it appears that it's not quite to spec, but nevertheless it's close to the 1500. It's not drastically different. Now if you are using one of these inverters for your house, just make sure that you want to buy one that has sufficient margin, not right at the borderline there. And for the next experiment, I hooked up this angle grinder, and it has a very high inrush current when it powers up. So we want to see if this inverter is able to handle that. And in the meantime, we also want to monitor the current waveform to see if there's any significant distortion there. So now you're going to be a little bit loud, but let me power it up. I will give you a warning. 3, 2, 1. Oh, sorry, 3, 2, 1. As you can see, it didn't have any issues starting up, but we did see momentarily that the output waveform is becoming distorted. So let me actually focus on the output waveform here. And you can see once we start the angle grinder what it looks like. So let's try it again. 3, 2, 1. Yeah, let's try it one more time. 1, 2, 3. So besides the little bit of distortion of the waveform at the very beginning when we start up the angle grinder, and the inverter itself handles the situation with no problem at all. And I went ahead using the data we just gathered during our test run and generated a output wattage versus efficiency curve. And as you can see here, it is rather impressive. At first, when I look at the specification, when it says it claimed that the output efficiency is generally above 90%, I was a little bit of suspicious of that claim. But now using the real data we just gathered, and you can see that that claim is not too far from the truth. For the majority of the data points here, you can see, especially between 200 watts and 1000 watts, the curve largely stayed above the 90% mark. So that's where the efficiency is the greatest of this inverter. And of course, towards the lower end and higher end, the efficiency drops off. And also from this curve, what you can see is that probably this inverter is rated somewhere at around 1300 watts rather than the 1500 watts it claimed, as the efficiency drops off. And of course here we got the cutoff that it warned us that it's exceeding its maximum capacity here. And from a power inverter efficiency perspective, this power inverter is definitely more efficient than the power electric one that I reviewed a while back. That one, if I remember correctly, is at a maximum of around 85% efficiency. And now it's time to open it up and take a look at the construction inside. And by the look of it, it seems that this is just a clamshell design, and we should be able to release the screws here and also on the other side. And hopefully we can open it up. Now I'm not sure what the screws on the sides are, but there's no screw at the bottom. So I assume once we open up the sides, we should be able to somehow open up the case. So let's give it a go. And okay, so now it seems I don't need to open this up, and I just removed all the 8 screws on the side, and I can actually lift up the top cover here. So now you can see the inside of this inverter. And by the look of it, in order for us to remove this board, because I want to see what are the power devices used on this board, and unfortunately on the side it's blocked by the case. So I have to actually take the screws on the side off. So not sure if you can see this, but the screws on the side are actually bolted onto the heatsink itself. So I don't think you can see it, but after I remove it, you will be able to see that. And anyway, so long story short is I need to remove these screws first before I can actually slide out the board from the case. At least that's the plan. And as expected, the whole board slides out from here after I remove the side mount that is mounted onto the heatsink itself. And on the bottom here, there's a piece of insulation paper that is preventing the board from touching the bottom. So now let's take a look at what is on this board. And just by looking at the board, we can kind of see the topology of how this inverter works. And towards the center on the board is our main controller circuitry. And according to the manual, that they use a customized chip. So I would assume that's the chip here because this chip has the marking sanded off. And the other two chips, unfortunately, I can't find out any information on that, but presumably this board is what is used to generate the modified sine wave and also used to control the remainder of the inverter portion. And if you follow the input battery leads, you will see that the actually battery leads divided into two sections. One goes into here and one goes into here on the right hand side. So these two sections are, by the look of it, is identical. Each has two 40 amps fuses, and these fuses are actually plugged into the board. So in theory, when the fuses are blown, you can replace them, but it would require you to at least open up the unit itself. But it is actually relatively easy to reach to these 40 amps fuses here. And so now if you take a look at the two transformers, each one is marked as 12 volts to 110 volts transformer. So these are actually the pulse transformers for the DC-DC converter that is mounted on this board here. And so if we look at on the side, you will see that there are two banks of these MOSFETs here, and each bank has 4 of them. These are, if I can read them clearly, these are IRF 1404. So these are actually 40 volts, 202 amps MOSFETs, and they're used for the lower voltage to the higher voltage DC-DC conversion here. It is interesting to see that we have 2 of these pulse transformers here, and without fully re-inverse engineer the circuit, we probably won't know exactly how they are working here, but just by looking at the bottom of the traces here, you can kind of see that at least 2 sets of these power FETs are actually parallel together, and so essentially these 8 MOSFETs form a bridge of some sorts and to drive the transformer. And if you look at the bottom of the transformer footprints, it looks like they're actually serves as a center tapped transformer just by the look of it, because these 2 pins belong to the 2 different transformers are actually linked together. So let's look at the bottom of the board. I wouldn't call this entirely clean. I would call it pretty messy, given that how much tin it is on each trace. Now, that is understandable because of the high current requirements on these traces. But if you look carefully, we also can see that there are some wires that is soldered on to each of the trays. And presumably that is there for increased current carrying capability as well. So in fact, you can see it on all these traces here. Besides the heavy tinning, you also have some kind of copper wire embedded on the trace. I'm not sure whether or not they're using 1 ounce copper or 2 ounce copper on this board design, but just by looking at the traces, how they did with the trace to increase the current capability, I'm guessing that probably the copper here used is 1 ounce. So this is to my earlier point, while it is convenient to use a 12 volt to power your inverter, but when your output wattage increases and you have such high current requirements, the inefficiencies of these traces, the resistance, no matter how minute, gonna add up to your power loss. So gonna decrease your overall efficiency of your inverter to some extent. So now let me flip it over and we can see the other side of the heatsink here. And on the right hand side here, these four are the STTH6006W. These are 60 amps, 600 watts, fast high voltage rectifier diodes. And to the left, these four devices are all IGBTs. And the first two on the left are FG 180N33. So these are 330 volts, 180 amps IGBT. These are N-channel IGBTs. And to the right, these two IGBTs are 85GT33SW. Now, I couldn't find any information on these two IGBTs, but presumably, because these are not the same as these two, I assume that they use two P-channel IGBTs for their output bridge configuration here. And the output from the IGBTs would then go through this choke here, and also this capacitor for they form a low pass filter so that the output would remain sinusoidal. And here is a better angle. You can see from the battery terminal how this wire is divided into two current paths and supply each of the inverter section here. So this kind of design by using wires to distribute the current evenly is fairly common for this kind of a higher current applications, as you wouldn't be able to push as much current through the copper on the PCB as you would with these thick wires. As you may have noticed, we have a thermistor mounted on the heatsink on the DC to DC converter side, but we don't have one on the IGBT output bridge side. I'm not sure why they would only use one of the thermistors, but not on the output bridge side. Presumably, the output bridge side probably is overspec'd, and that's just totally my guess. It doesn't, the temperature doesn't rise as fast as the lower one. So the theory goes, because these two sections are essentially in series, so if the lower section is overloaded, then we will cut off the entire circuitry. But in theory, the output stage would never be overloaded unless the lower DC-DC converter section is overloaded. But if I were in charge of the design, just for redundancy, I would add a thermistor on the output bridge side in addition to the input DC to DC converter side. And if you look carefully, you will see some interesting constructions here. And if you look at the section here, there are a few caps mounted on the board. But if you look at it, some of these caps are mounted on top of each other, and because the footprint does not allow them to be mounted in parallel, that is very interesting. And if you look to this side, you will see we have two more vertical boards. And I'm not entirely sure what these vertical boards are for, but the one to the back here, that's definitely for the beeper. And the one here, by the look of it, it's another DC to DC converter module, as it has a MOSFET here and it has a little transformer. So not entirely sure what this board is doing here. And if you look at it actually from here, you can see they did use some kind of quality parts, and the caps here, by the look of it, are Nippon Chemicon caps. So those are certainly good quality caps. And in general, the board looks very, very clean, the design, so can't fault too much on that. And to reduce cost, they're using some of the off-the-shelf components here, and you can see here the output voltage and current measurement meters are both these 3.5 digits off-the-shelf components. And everything that shakes and moves, and you can see here, are either glued down or tied down, so that's pretty secure here, and no complaint at all. And by the way, and from what I can see on this beeper board that I mentioned earlier, it has a trimpot here, so by the look of it, it probably is used to control the over voltage and under voltage adjustment here. Overall, the build quality is not bad at all. Now it's time to put everything back together. So from my testing and teardown, I think this CNSWIPower Pure Sine Inverter is a pretty good one, especially given its high conversion efficiency. Of course, the only downside is that the power rating is about 200 watts less than what it claims. You should bear that in mind when choosing yours. You should be provisioning at least 50% more than you need. I hope you enjoyed the video and found it useful. If you liked the video, please remember to give it a big thumbs up and remember to share and subscribe. I will catch up with you next time.